Again, it's a red stick.
What is going on, guys? Welcome back to the Algorithms and Data Structures tutorial series. In today's video, we're going to talk about merge sort, which is the first divide and conquer algorithm that we're going to look at. And it's also the first efficient, quote unquote, efficient sorting algorithm that we're going to look at. So up until now, we looked at bubble sort, insertion sort, selection sort, and now we're going to look at merge sort. In the next episode, we're going to look at quick sort. And we're going to start to look at these more efficient divide and conquer algorithms. So let us get right into it. So let us start by talking about the divide and conquer approach because we haven't covered it yet. And the divide and conquer term is a military term, and it comes from the idea that if you have an opponent that's too big, what you do is you divide them, you divide the people, you divide the armies into small sub-armies and conquer these armies individually. So the total result in the end is that you won the overall battle, even though you just conquered small armies. So if someone has 1,000 people, for example, you just split them up into groups of 100 people 10 times, and you conquer these 100 people 10 times, and in the end you won the overall battle because you conquered these 10 groups of 100 people, whereas you were not able to conquer the 1,000 people in one battle, right? And this is an approach that we also have in computer science, of course, not in the military setting, but in a programming setting. What you do when you have a complex problem is you divide it up into sub-problems. So you have one big problem here, one problem, and it's too big to be solved efficiently. You can solve it in quadratic time, cubic time, whatever. And what you do is you split it up into a couple of sub-problems here. Sub-problem 1, sub-problem 2, sub-problem 3, and so on. And what you do in the end is you conquer all these, you solve all these problems. Or maybe what you do is you split them even up into more sub-problems, right? And then once you have solved all these small sub-problems, these sub-problems are so simple that they can be solved easily. Then you combine all these sub-solutions into a solution to the whole problem. This is the idea of divide and conquer, and this is why we can sort in n log n time, in so-called pseudo-linear time, because we make use of this divide and conquer approach, which is also what we do with merge sort. Because when we have a list, 4, 8, 7, 1, 5, 6, 2, 3, or whatever. This is the list. What we do is we don't sort in a linear way. We don't sort the way in the same way that we do with bubble sort or insertion sort. We don't just pick a number and compare it to all the other numbers, but we take this list and split it up, for example, into two lists, then split this up into two lists, and so on, until we have a problem size that is so small that we can sort it efficiently or easily. And then we get these sorted sublists and combine them together. This is what we do in merge sort, and we're going to talk about this in more detail right now. So now let's look at what merge sort actually does. We're going to write down merge sort is what we're going to look at, the divide and conquer algorithm merge sort. What we do here is we have a list of numbers, again, something like 7, 3, 6, 8, 4, 1, 2, 5. This is everything, yes. So we have this list, and this list needs to be sorted. So what we do now is, or what merge sort does now is, it splits the list into two parts. So into the left part and the right part. Then we have 7, 3, 6, 8, and 4, 1, 2, 5 as separate lists. So what we do is we write them down, 7, 3, 6, 8, 4, 1, 2, 5, and then we recursively call merge sort onto these lists. So now we don't care about this right part. We call the whole merge sort algorithm onto this list here. And what this means is, of course, that we split it again. So what we do is we split it here in the middle again. Same goes for this list. And then we split this up into 7, 3. So 7, 3 is one list, 6, 8 is another list, 4, 1 is another list, and 2, 5 is another list. Then again, we call merge sort onto these lists, and we split them up into two halves. And we end up with 7, 3, 6, 8, 4, 1, 2, and 5. So this is what we do. We have this tree here, this divide and conquer tree, where we split these lists up into two parts with each iteration. Or actually not iteration, but recursion. So what we now do is we have 8 lists with one element inside of the list. And what we do now is this is the divide process. This is what we call divide. We get the list and divide it into sublists. And now we can start with conquering. So what we do now is we'll look at these two lists here, These are two separate lists, and now we conquer them, so we sort them. And obviously 7 and 3, it's easy to sort this list. So what we do is we just combine them into a sorted list by saying, okay, it's 3 and it's 7. This is the one list. So we end up with the list 3, 7. This is the sorted list. We do the same thing for 6, 8. So it's 6 and 8. We do the same thing with 4, 1, 1, 4. 2, 5, 2, 5. This is how you merge them. This is the process of merging. You have two lists and you merge them. Now it's very simple when you have just two elements, 1 and 1. So you just have to compare those and you're done. But it's also not very complicated when you have more elements, because what you need to do now is you need to think about it. All these lists that you have here are already sorted. This list is sorted, this list is sorted, this list is sorted. All these lists are sorted, okay? So you don't have to worry about this number being larger than this number. You know that the lists are sorted. So whatever you want to do now, you know that these lists are sorted. So if you want to combine, if you want to merge these two lists here, 3, 7 and 6, 8, what you do is, in order to figure out what's the first element, you just have to look at the first two elements. So at this one and at this one. You don't have to consider 7 and 8 because you know 7 and 8 are not the smallest value. So what you do is you pick the 3 in this case. So let me choose the yellow color again. Yeah, the 3 in this case. And then what you do is you only compare 7 to 6 because you know 8 is not going to be the smallest value again because 6 is definitely smaller than 8. Even though you don't look at 8, you know it because the list is sorted. So what you do then is, okay, 6 is the next one. Then you compare 7 to 8. It's 7, 8. And then you do the same thing here. 1 or 2, it's 1. 4 or 2, it's 2. 4 or 5, it's 4, and then 5. And then you do the last merge here by comparing these two lists. So again, you just look at 3 and 1. You don't have to consider all the other numbers. You pick 1 as the first value because it's smaller. Then you just look at 3 or 2. You pick 2. Then 3 or 4. You pick 3. Then 6 or 4. You pick 4. Then 6 or 5. You pick 5. Then 6, 7, 8 is already sorted. This is how you merge the list. And as you can see, this is a way more efficient way because you don't have to compare all the elements. You just compare the first two elements of the list or the first two elements that are left in the list in order to figure out how to sort the list. This is the process of dividing up until here and then conquering or merging. So you can say you're dividing the list, the problem size here, and then you're merging or conquering down here. Conquering. This is what merge sort basically does. So let's go ahead and now analyze the runtime complexity of the merge sort. For this, we're not going to look at pseudocode because it would be unnecessarily complex to do that. We've done enough calculations. If you're interested in doing that, you can just type merge sort pseudocode. You're going to find a lot of resources on that. It wouldn't be very beneficial to you to just go ahead and analyze the merge sort again. We can do this with intuition as well because the merge sort, it's easy to understand. You can look at the code, you will understand it probably. But it's not necessary to analyze it by looking at each line of code because we can just intuit ourselves, intuit our ways into the runtime complexity of merge sort. It's not that difficult because what do we do here actually? We have 3 steps. First of all is we have the dividing. This is one thing. This is one part of the process. We divide the total list. Then we have the recursive call. Recursive call. And then we have the merging, right? The conquering, the merging, whatever it is, right? And what we need to do is we need to figure out what the runtime complexity of these 3 things is, right? And the first thing that we do is we divide. We have the full problem size n. We have n elements here. And then we have n half elements per side here. Then we have n divided by 4 elements and n divided by 8 elements over time. And essentially we do this until we get to single elements. So if you have 16, you're going to divide 1 more time. If you have 32, you're going to divide 2 more times and so on. You're always going to divide the list until you get to single elements, to separate elements. And this is also true if the number of elements is not a power of 2. So if you have like 7 elements here, it's also, you can also go ahead and split into 2. The point is if you have a list like 3, 2, 5 and you divide it, you're going to say, for example, here is the middle, or here you can decide. And then you have 3, 2, 5, and then you have again one more time 3, 2. Oh, sorry. You have 3, 2, and 5 separately, right? So how many times do we need to divide the list in order to get to single elements? It's essentially just the logarithm of base 2 of n. Because you have n elements, and how many times you need to divide n by 2 in order to get to 1 is the exact definition of logarithm. So formulated the other way around, it would be how many times do I need to multiply 2 by itself in order to get to n. This is what logarithm base 2 basically means. And this is the answer here, right? So we have 8 elements, and 2 to the power 3 is 8, so we have 3 levels, or 3 times division. 1 time, 2 times, 3 times, right? So this is how you divide it. You have a logarithmic runtime complexity when you divide the list, when you split it up. Of course, if you have 16 elements, it's going to be 2 to the power 4 and so on. And again, also if you have 7 elements, it's also going to be 2 to the power 3, because 8 is the next power of 2 that comes after 7, right? So we're not only interested in the exact value, but also in the next, we're actually interested in the next power of 2 in this case. So this is the first thing. This can be done in logarithmic time, right? And then we have the recursive call that essentially calls the merging process. So we're done with the splitting, where we have the individual elements here, and now we want to merge them. And let's first talk about step 3 here, the merging. How many operations, or what runtime complexity do we have when it comes to merging? Let's look at the last level here, that we have 3, 6, 7, 8, and 1, 2, 4, 5. Now in the worst case, we need to merge, or we need to have a linear amount of comparisons. Why? Because I need to compare the first element of this list with the first element of this list. And I need to do this until I have all the elements down here. So in the worst case, I have linear runtime complexity. And this is true for every merge. So we can say that this can be done in linear time, at least in the last level, but this is also the case for the formal levels. Because if we have 3, 7, and 6, 8 here, the runtime complexity is still linear, but the problem size is a different one. So in this case, we have 4 elements instead of 8 to merge. Sorry, I'm always clicking this button here. We have 4 elements instead of 8 to work with, but at the same time, we have this 2 times. So we don't have 8 elements, we have 4, but we have 2 times 4. So we have 8 in total, which is still linear for this level. And then we have here 2 elements, but we have this 4 times. So we have 2 elements here, 2 here, 2 here, and 2 here. So we always have n merging operations, or a linear runtime complexity per level. So we have linear time here. And if this was everything that we need to consider, it would be a linear runtime complexity. But the point is, we do recursive calls, and we do the linear operation as many times as we need to get back to the full list size. So the dividing is logarithmic, but what we divide, we need to merge again. The merging is linear, but we need to merge as many times as we divided in order to get to the full list size again. So we have a logarithmic split, then we merge them, and we need to do this merging as many times as there are levels. As many times as we divided the list, we need to combine it again. So in total, we need to do this linear process logarithm of base 2 of n times. So the full runtime complexity in the big O notation is the logarithm of n times n, which is pseudo-linear. Because the process of merging is linear, but we need to do it as many times as there are levels, which is logarithmic. So pseudo-linear runtime complexity. So that's it for today's video. I hope you enjoyed it, and I hope you learned something. One more thing that I want to mention about the merge sort algorithm is that its runtime complexity is the same for the best case, for the average case, and for the worst case, because it always does the same operations. It always takes the list, splits it up, and then merges it together. So you always have this merging process log n times, log 2n times, no matter if the list is already sorted. So even if you give the list 1, 2, 3, 4, 5, 6, 7, 8 to the merge sort, it is the same runtime complexity because it's going to split it up and combine it back together. So you can definitely be sure that you're always going to get pseudo-linear runtime with merge sort. So if you like this video, let me know by hitting the like button, leaving a comment in the comment section down below. Also, make sure you subscribe to this channel to see more future videos for free. And thank you very much for watching. See you in the next video. Bye.